Okay, we are going to start chapter 3 today in this video, and it's going to be a rather short lesson because this is just sort of a rehashing of what we talked about when we talked about lines. A line, of course, is a graph, and a linear function is just a function whose graph is a line, basically. And the official definition, it's just what you'd expect. A linear function is a function of the form f of x equals mx plus b, where m and b are constants, or m and b are real numbers. And the graph of that would just be y equals mx plus b. So it's a line. The slope is going to be m, and the y-intercept is at b, okay, which we sort of already knew. The domain is, they're all real numbers because we can plug any real number we want in for x. The average rate of change, not surprisingly, is going to be the slope, which is m. And it's going to be the average rate of change over any interval. It really doesn't matter what interval we pick. Okay, the change in y divided by the change in x is always going to be the same. And like I said, that's the one feature that lines have that's different from any other graph. And that's the one feature of the linear functions have that's different from any other function. So as a result, okay, the linear function is either going to be always increasing or always decreasing or always constant, depending on what the slope is. If the slope is positive, the function is increasing. If the slope is negative, it's decreasing. And of course, if the slope is 0, the function's constant. Okay, and just to show you some real simple examples, if we look at this function, f of x equals minus 3x plus 7, I plugged in some of the basic values for x and got the values for f of x. And we can see that between, if the change in x is equal to 1 in all the cases, we can see the change in f of x is, well, here it's going to be minus 3, here it's minus 3, here it's minus 3, here it's minus 3. Okay. So that will just keep going forever. We want to plot these. Okay. We can start with the y-intercept, which will be at 0, 7. And we could plot these points. For example, 1, 4 is up here. And we could continue this. But we can see that these 2 points are really all we need to determine the line. So we can just draw this line segment and then extend it down. Okay, if you're good at, and extend it up if you're good at drawing straight lines. Okay, not too much there. So basically you just need 1 point and the slope. Okay, so want to try this next example on your own. If you wanted to sketch the graph of f of x, where f of x is 5x minus 4, I'll let you do that. You can see that the slope is going to be 5. The y-intercept is negative 4. Obviously, this function will be increasing everywhere, and the y-intercept is negative 4, so we can go down here. And then from here, we can just go, the slope is 5, so we can go up over 1 and up 5. So it's 1, 2, 3, 4, 5, and over 1. And we get that line right there. Okay, so the next example, we're really going to talk about the intersection of 2 lines. We've already done this. We're just rephrasing this as kind of a just in terms of algebra. Here we have 2 linear functions. We want to know where they're equal, so we can set them equal. And then we can add 2x to both sides, add 1 to both sides, and we get 6x plus 0 equals 0 plus oops, we want this to be a plus 1 here. So it's 6x equals 6, divide by 6, we get x equals 1. And we can see that then indeed is going to be a solution. We can plug this in both cases, in both expressions, and we see they're equal. We'll come back to this in a minute. If we wanted to solve the inequality, we can see that we can basically do the exact same thing where the equal sign is replaced with a less than or equal sign. Because when we get down here, so again we could write 4x minus 1 is less than or equal to negative 2x plus 5. Do the same, add 2x plus 1 to both sides, so you get 6x is less than or equal to 6. And then because we don't have to, we divide by 6, and 6 is positive, we don't change the direction of the inequality, so the answer is going to be x is less than or equal to 1. Similarly here, we can, if we wanted to set, when f of x is bigger than 5, we would say 4x minus 1 is greater than 5. Add 1 to both sides. 4x is greater than 6. Divide by 4. And so x is greater than 6/4, which we can reduce to 3/2. So the solution would be x is strictly greater than 3/2. And one other thing here, we can graph this to sort of visually see it. We graph both lines associated with these functions. We know that the point of intersection is at 1, and if we plug in 1 here, we get 4 times 1 minus 1, that's 3. So the point 1, 3 is the point of intersection. Just say f of 1 is equal to 3, and also that's also equal to g of 1. And we can plot these other lines. We know for f, for the graph of f, the y-intercept is -1. So there's this line. For g, the y-intercept is at 5. Okay, so this is the y equals f of x. This is y equals g of x. And we can clearly see here's 1. When x is less than or equal to 1, we can see that this line is certainly bigger than this line. The graph of that is the graph of f is above the graph of g is above the graph of f. So g of x is greater than or equal to f of x on this interval from -infinity to 1.